So today we have Dr. Vivian Yu, who's visiting from the University of California, Irvine. She earned her PhD from the University of Hawaii, and then was a TNT postdoctoral fellow at UC Riverside. She followed that up with the University of California Chancellor's Fellowship, which split, I guess, between Riverside and Irvine, although now she's fully at Irvine. So Vivian studies supermassive black holes and tries to understand the role that they play in galaxy evolution. So we're going to hear about various aspects of that today. So welcome.
Thanks, Jeanette. Thank you so much for inviting me here today and giving me the chance to share my passion on understanding supermassive black holes with you all. I'd like to start off with this image, spectacular image of the UDF, because it really was what sparked my interest in observation extragalactic astronomy, and it's also kind of signified my personal start of the journey in the field. And it really shows that galaxies, which are the basic building blocks of the universe, come in different flavors. And they tell a story of how they've formed and evolved since the beginning of time. And so I'd like to be part of this quest in trying to decipher the assembly history of the universe. Now, a lot of people have obviously put together the large pieces of puzzle before me. And so here I'm showing the star formation rate per co-moving volume as a function of redshift. And you can see that star formation activity peaks around Z2, around cosmic noon. And if you break that up into different galaxy populations, you would see that beyond a redshift of 0.7 or so, the star formation rate density is actually dominated by these galaxies called luminous and ultraluminous infrared galaxies in the orange and the red. And so just what are these lurks and U-lurks? And what is the role that they play in galaxy evolution? Some 30 years ago, when these lurks and U-lurks were first discovered by the IRAS satellite, my PhD advisor, Dave Sanders and company, had put forth a theory for the role of these galaxies in galaxy evolution. So you start off with these blue gas-rich star-forming spiral galaxies, and then they come into contact with each other, and they do this delicate dance before becoming a gravitational bound system, and eventually merging. And all this time, the gas and the dust material is being funneled into the center of the system to fuel the nuclear activity from the interaction. And all that starburst that's from the optical light is actually getting reprocessed by the dust, so that these galaxies appear to be luminous in the infrared. And eventually, all of that gas kind of gets funneled in the center of the system, and then they trigger the AGN and releases energy so much that it kind of removes gas from the rest of the galaxy, and depending on who you talk to, they probably end up with these red dead elliptical galaxies that are just passively evolving. Now, the theorists have put this together in a time scale so that we can understand that this whole emergent process takes place over the course of several giga-years. But in particularly, these very ephemeral stage of the galaxy's lifetime, these galaxy mergers, are actually the stages that represent a lot of activity happening at the star formation activity level as well as the black hole growth. And so it's these transitional objects that I really focus my research on to understand their place in galaxy evolution. So at the same time, we see that the mass of the black hole actually correlates really well with the properties of the galactic bulge that they reside in, telling us that somehow the supermassive black holes and the host that they reside in co-evolve, despite their the drastic difference in their size. And the terms feeding and feedback have, of course, been invoked to try to understand this relationship between the two. But exactly how they interface with each other is still a lot of details that we don't really understand yet. So if you really want to understand what happens when galaxies merge and also when the supermassive black holes merge, you need to understand and study these gas-rich late-stage mergers, particularly because they host these nuclear disks that are about 100 parsecs or so in size that we've seen in both simulations and observations. And these are also going to be the circumbinary disks that host supermassive black hole mergers that will be detected by the next generation gravitational wave detectors. So that might be intriguing for that reason as well. But the bottom line is that we need to understand the small scale environment that host these coalescence events. So to really understand what happens with galaxies and supermassive black holes coevolution. So the key question that I like to address is how do supermassive black holes grow and merge? And given the dynamical scale that's involved, I like to break this question and also this talk down into two different regimes. So for scales up to about kiloparsec or so, we want to know how the gas actually fuels supermassive black hole growth. And how do the accreting supermassive black holes actually impact the surrounding star formation? And on a much smaller scale, how does that black hole accretion affect the broad-line region structure, and how does that actually come about? Okay, so let's start off with this first part. So I wanted to show this picture because I want to show the scale where you can see when I talk about the inner kiloparsec region of a galaxy merger, what I'm really talking about. So it's really just the central part right here. And perhaps you might ask, legitimately, why does the gas even matter from this, from this small region, even matter in the grand scheme of things? And so the answer is you need to think about the galaxy not as a static structure, but rather as a dynamic ecosystem. So within a galaxy, you have your interstellar medium, and that fragments and form your giant molecular clouds. And then using your favorite stellar evolution, they form stars, they go supernovae, and that would drive winds into the interstellar medium, and then that eventually cools the gas and probably have the gas fountains back into the galactic disk. Perhaps you will also get some additional accretion of cold gas from the large-scale filaments as part of the gas reservoir. And some of that gas obviously can also go into the center to fuel the central AGN or the nuclear star forming activity. And that in turn can drive even more outflows. And if that's powerful enough, you might actually just remove all of the gas and quench star formation. So the merger process, actually how that contributes to some of the components within this ecosystem is not entirely known. And we want to figure out exactly the time scale of how things happen, how quickly things happen, and also the amount of energy deposition and the mass that's involved in this whole process, and to really appreciate what kind of influence mergers has on galaxy evolution. And of course, this process is very complex. Also, here is attacked by some theorists using, for instance, fire tube simulations. In particular, this is modeling the ISM, and the different colors here represent different gases of different temperatures of what happens in this merging process. Now, in this particular set of models, I think AGN feedback isn't actually incorporated because of the complexity of the physics involved. But it is this sort of simulations that require us to have really good high-resolution observational constraints to understand the type of AGN feedback that is being involved. So fortunately, for me at least, that we live in an era of high angular resolution studies across the entire electromagnetic spectrum. So here I've highlighted some of the resolving capabilities of different telescopes across from X-ray to the radio. But really in this talk I want to highlight work that's been done using the ground-based AO system, particularly those on Keck. So I want to actually first demonstrate what we can learn using this sort of near-infrared IFU data, and go a lot into detail of how we've been using it. So here is my Karen 273. It is my favorite pet ruler. I believe everyone should have one. And it is clearly a late-stage merger with a very complex nuclear region in the center. And so here is a integrated H-band spectrum. And if I slide across this particular spectrum over the iron 2 line, you can see really well how the iron 2 gas actually is rotating. So projecting this onto 2D form, you can see the flux distribution of that iron 2 gas on this left panel, actually peaking at this cup right here, and the continuum is from the H-band, the contours are from the H-band continuum. And actually, you can see a very compact near-infrared source in this region of the field of view. So this is the morphology of the ionized gas, iron 2, at 1.64 microns. But interestingly, you can see also from the kinematics map that it actually really depicts that rotation of the disk that we see in this galaxy. And because of the resolution that we have, about 28 parsecs per pixel at a ratio of 0.04 for Vivian091619, we're resolving within this black hole sphere of influence, and then we can make some estimate of the dynamical black hole mass. So by modeling the rotation in this galaxy, we were able to derive a black hole mass of about 1 billion solar masses, which is actually consistent with an earlier estimate from O.H. Mazars. Now, I will mention that there are obviously experts in this room, Janelle, Ben, and others who have been doing this, with more precise and accurate data and measurements using high-quality near-infrared IFU data, ALMA data, and also very sophisticated models. But extracting useful kinematics from the messy cores of mergers is a really kind of different type of challenge in this game. And so we're doing the best we can, and so that we can actually start to understand what role mergers play in this process. And so I show this M sigma plot from the beginning, and now we can actually place mergers on this plot because we want to know if most of the galaxies follow this relation, what happens when galaxies merge with each other? Is it a case where the black holes might grow first, and then the bulge catches up, or vice versa, or do they grow at the same time? So when we finally put our mergers on this plot, we have found that they basically lie on top of or above the scaling relations. So we favored a couple interpretations. One is that maybe the supermassive black hole growth is taking place faster relative to the bulge, and this is potentially because the merger funnels the gas in very, very efficiently, and so the black hole actually grows pretty fast. Or we actually have large reservoirs of gas just sitting near the black hole, but within the sphere of influence waiting to be accreted. And that's something we're kind of trying to resolve at the moment with high-quality ALMA data. But, and there are also other caveats with the plots if you're interested. I can go into after the talk. But basically, this is what we're seeing with the earlier part of our campaign where we had just under 10 galaxies. We've since then tripled the number of data points that we've had, and we hopefully will be pushing out a revised version of this plot shortly. But what's more is that aside from black hole masses, we actually were able to learn a lot of other things from the near-infrared OSIRIS data, where we probe primarily in the K-band. So in the K-band, you actually get a suite of near-infrared diagnostic lines, including molecular hydrogen, which is about 2,000 Kelvin or so, and also the hydrogen recombination lines like bracket gamma, bracket delta, and then also other species like helium-1, silicon-6, etc. And you can see that, of course, with the IFU, that the line ratios as well as the continuum level really changes depending on the field of view, or the position within the image. So when the character 73 with multi-wavelength data from literature, previously, all we could say was that there was AGN based on relatively shallow 44 kilosecond Chandra data, that the AGN sits in this southwest spot that I pointed out as a very compact near-infrared source earlier. And it wasn't until our Keck data that we can say there's actually an additional remnant nucleus sitting in this center of this galaxy, making this a dual system. And then that dual nature actually got confirmed by deeper 200 kilosecond Chandra data that we got much more recently. So you can see how having that near-infrared gas dynamics is really important for finding and validating the dual nature of supermassive black hole mergers. But not only that, when we looked at, actually this is now switching to molecular gas, molecular hydrogen, flux and velocity dispersion maps, you can actually see some enhancement in the velocity dispersion along the minor axis of that disk. So we interpreted this as the first, as a smoking signature of the biconical molecular outflows coming out of this rotating disk in this galaxy, for this galaxy. So this is the type of the nuclear outflows that we can see, that we can only see with observations of this high resolution only. And so we were able to compute the velocity, the mass, and the energetics for this outflows, and actually using these as quantitative comparisons to the simulations at these tens of parsecs resolution. Now, that was one galaxy that was really nice, it was really encouraging. We've actually looked at a bunch more of the galaxies in the merger sequence so that we can try to learn what the detailed gas and stellar kinematics is as this merger progresses. And so together with my collaborator Anne Medley and the GOLS team, we have now gathered search data for about 30 nuclei in 20 subsystems. And if you're interested in the data, feel free to check out our website. But in summary is that our data covers about 26 merging systems, about 30-some nuclei at redshift 0.03 or so, all resolved at tens of parsec resolution. Now, I won't go into the specific science highlights of all of our survey results this far, but our latest survey paper actually focused on determining the star formation rate and also feedback of this survey. So we were able to see for extinction corrected star formation rate that they do in fact increase with merger class and also decrease with projected separation between the nuclei. And also we found a lot of shocks as indicated by excess molecular hydrogen in our AGN hosts. But when we try to understand what might be driving those shocks, we actually see that they're not really correlating with the AGN strength as measured by the mid-infrared or the volumetric AGN fraction very well. So there must be a lot of other factors like dust patchiness involved in terms, and geometry involved in terms of understanding what is driving the shocks within these really obscured regions. And so that's kind of the reason why I might be really excited about JWST is that one is hopefully on the horizon, hopefully. And two is that it actually will provide an order of magnitude or two more sensitive at 2 microns compared to Keck, and also at 10 micron compared to Spitzer, so that this will be huge. You know, that allows us to really peer through the dust in these really obscured extincted regions. And what I'm most actually excited about is that we're putting a mid-infrared IFU in space for the first time. So MIRI, the mid-infrared instrument or JWST, is going to probe a slew of features, so pH features and also some cooling gas features. This is about hundreds of Kelvin or so that are really prominent in the infrared. And so with our ERS program, where the GOLS team is going to be looking at 4 particular nuclei of these lurks and U-lurks that span a range of silicate strengths. And the idea is that we will hopefully tease apart the multi-phase chemistry and also looking at the dust and getting this complete picture of feedback at these kind of unprecedented scales in the local lurks and U-lurks. Okay. So just to wrap up this part of the talk, I hopefully have convinced you that we were able to have some insights on very small scale feeding and feedback processes based on our CERS data. But most importantly, we're actually looking at how the supermassive black holes and the galaxies interface with each other at tens of parsecs resolution in a systematic manner. Okay.
So can I ask a quick question?
Please.
So from the survey, do you have multiple dually gene candidates that you're following?
So right now we're not doing additional follow-up, but I think in the entire goal sample, which is about 200 of the local lurks and ULurks, there might be like 4 cases or so. And McKeown 273 is probably one of the ones with one of the smaller separations. Okay, so let me now switch gears a little bit for a more zoomed in view into the AGN, but I would say not quite at the resolution of EHTs. So here is the canonical picture of an AGN. Of course, you have the black hole sitting in the very center, surrounded by the accretion disk, and you have gas particles that are moving really fast due to the gravitational potential of the supermassive black holes in this broadline region. And all of that might be obscured from view by the torus that you can see here. Now, I've just told you that with state-of-the-art instruments on 10-meter class telescopes, we can barely probe down to the tens of parsec scales at a distance of less than 0.1. And if you work out the math with diffraction limit, even with 30-meter class telescope, you're not going to get down to these scales. So what do we do in the meantime is that instead of trying to resolve things spatially, we try to then resolve things temporally using reverberation mapping. So reverberation mapping is a time domain astronomy technique that relies on the fact that the AGN in the center of this galaxy, of the system, is a stochastically varying source. So if you have the light from the accretion disk coming to you as the observer, either coming directly to you, or it can get bounced off some gas particles in the broadline region, and it comes to you after some time delay. And if you monitor the light signal from the accretion disk by looking at the continuum, you might actually see a similar, hopefully similar, signal in the broadline region that's reflected in the gas. And so if you were able to correlate those signals and actually measure the time delay in between them, then you can essentially have a measurement of the average size of the broadline region based on the fact that light's travel time is finite. Now, that's actually the fundamental quantity that you measure, but of course you can then also measure the velocity of the gas particle in the broadline region, and then invoke the virial theorem, and then have some estimate of the virial mass of the black hole, modulo some F factor that depends on the geometry. So to formulate this a little bit, the signal that you see in the line as a function of the line of sight velocity and the time is really just a convolution of the continuum with the transmission function that also can be expressed as a function of the line of sight velocity and the time delay. So that is actually what I'm most interested in, is what's called the velocity resolved reverberation, because if you look at these velocity delay maps showing time delays as a function of velocity, you can basically get a sense of the qualitative description of the gas kinematics within the broadline region. And I'll talk a little bit more about that in just a few slides. But one of the most important results that came from reverberation mapping is that we found that the broadline region size actually correlates really well with the luminosity of the AGN at 5100 angstrom. And so this relationship, this radius luminosity relationship, gives us a way of measuring single epoch black hole masses out to high redshifts, because all you need is an optical spectrum, a rectified optical spectrum of some distant quasars. You can measure the 5100 angstrom luminosity, and then you can get a size of the approximate size of the broadline regions as we described it. Now, of course, the uncertainty is going to be maybe a factor of several because of all those geometry assumptions that I might have talked about. And also, it's, this assumption that the virial theorem works may not actually apply to all of the black hole demographics that we see between now and beginning of the universe. And so what we really need to know is whether or not those virial assumptions actually could be true or applicable for large black hole demographics. And so I came into this project being really interested in trying to characterize the Brownian region gas structure for a wide range of AGNs. So I joined this lake AGN monitoring project a few years ago to really try to improve black hole scale emulation. And this is a large team of folks who actually either help us contribute their effort and time to do our spectroscopic monitoring observations, and also there are folks who contribute their telescope time from all over the world. So on the radius luminosity relationship, this is sort of the regime that was previously probed by previous campaigns of the LAMP project. And with our new goal, we basically want to measure velocity resolved flags, and hopefully that would allow us to do dynamical modeling down the road as well. And I'll mention that there are only like a handful of objects with these velocity resolved measurements, like 15 or 16 unique objects if you look through literature. And so in the new campaign, we basically selected a region that's not the most luminous in this luminosity axis, but also this is where we're lacking a lot of the good velocity resolved measurements to look at Brownian region kinematics. And we've looked at about 21 AGNs. These are what the AGN optical spectra look like from our 100-night lake campaign using the cast spectrograph of a 3-meter Shane telescope at Lake. You can see the H beta and O3 lines in blue and the H alpha lines in red. And so our cadence of 2 nights a week, we observe 12 to 15 objects per night. We're able to achieve a continuum signal to noise of about 100 at 55 angstrom. And if you wonder how well our sample varies in terms of light signal, so here's actually the photometric light curves that were put together by our previous undergrad at UCI, Alex Vogler, who combined all of these light curves from different telescopes, and you can see really nice dips and peaks actually in our light curves that we need to for our correlation signal to study to be done. So of these, we were able to put together about 17 objects that actually had measurable integrated lags. And so you can see that they mostly fall within the scatter of the radius luminosity relation from literature. But I told you the thing that I'm most interested in is actually the kinematics, the velocity resolved kinematics of those of these black holes. So to demonstrate what that looks like, here is a velocity delay map, like what I just showed you. This is a symmetrical velocity delay map, and what that means is basically that the BLR is probably experiencing either Keplerian rotation or just net random motion with no net radial inflow or outflow. And so the other types of velocity delay maps might include the following. So in the infalling case, where if you have gas that is moving away from us, and that's on the near side, you're going to get, and this will be redshifted, which corresponds to the redshift side of the line having the shortest lag. So in the opposite case, in the outflowing case, then you actually have gas moving close to us that's coming towards us, so blue shifted. So you have the blue side of the line that has the shortest lag. And then there's some ambiguous cases. And so I want to emphasize that this is really a simple qualitative description. This could be muddled by like absorptions in the Brownian region and stuff like that. But this is kind of a first look at seeing whether or not the gas in the Brownian region is actually moving virially. So if I were to color code our sample on the radius luminosity relation by the different BLR kinematics, you can see that there's a diversity in the Brownian region kinematics, and that possibly maybe depends on the luminosity with the more luminous stuff having outflowing gas, etc. However, if you put in the rest of the measurements from literature, this luminosity-dependent trend seems a lot less clear-cut. And so, one thing I'm currently investigating is whether maybe this is not a luminosity-dependent trend, but it might be depending on the AGN accretion rate, for instance. But I think this gives us a lot of leverage to try to start to look at why, how that AGN structure actually comes about. Okay, so all in all, our 100-night reverberation mapping campaign with Lake was able to test these Faro assumptions and actually reveal diversity of these raw language and gas kinematics. And we have basically doubled the number of existing sources with these velocity-resolved lags so that it could enable us to do very more accurate, dynamically measured black holes down the road. Okay, so in the last few minutes of the talk, I want to go back to doubling the fun and talk about dual black holes. So as an observer, I'm rather looking forward to the next observational frontiers that are coming up. As a couple of esteemed astrologers on Twitter have pointed out, we're rather excited about some 6.5-meter Ouija board or some large crystal balls. So I've talked a little bit about the Ouija board already, so let's focus on crystal balls here. I think with this audience, I don't need to really introduce the 30-meter class extremely large telescopes. I personally got involved when I was a TNT IRMS postdoc doing exposure time calculations and doing some data simulations for the anal-assisted spectrographs on TNT. And I've since then stayed within the US ELT community to try to wave the flag for the Cato survey white papers on support for these US ELTs, particularly on dual AGN and binary supermassive black holes, that I think would be a very interesting breakthrough science case for the US ELTs. So from the electromagnetic point of view, what we want to know about these merging supermassive black holes is, what kind of nuclear conditions leads to these coalescence events. And if we want to know the merger's importance, we need to understand the merger contribution much better than we do now, and what kind of timescales are we talking about, and how often do they merge? Can we actually try to locate, identify, verify these dual candidates based on larger galaxy properties? So in the binary cases where the separation between the black holes might be less than 10 parsecs or so, there have been several cases that were posited. I would say that really only one bona fide case kind of stands out and has the consensus of the community, and that remains the 4C plus 37 object that was resolved by VLBI imaging to have a nuclear separation of 7.5 parsecs. And the dual cases where we have black holes that are maybe of separation up to a kiloparsec, here's one of the most famous cases, NGC 6240, which has a dual AGN with separation about a kiloparsec, and it's a borderline Euler. But the question is, can we actually find more of these cases to say how many black holes actually merge in the long run? So I showed this plot in the very beginning of my talk to motivate how new lurks are important, especially at high redshifts. But the question is, when you get to high redshifts, it's actually not as clear-cut that the Euler population is dominated by mergers, like it is in the local universe. But there's work that is starting to understand the process. So here is a plot showing fraction versus inferred luminosity. And so if you look at the green line, which is the merger line, at redshift of about 1, you still get about 50% of the Eulers that are likely to be mergers or have some sort of irregular shape. So hopefully there are these mergers out there. Now the next question is, can we actually find them? So here is a Muse data cube of a Z of 0 dual AGN case with separation of 4 kiloparsecs, and I just clipped this around H alpha and 2. And so I did a really quick and dirty simulation to see what this would look like with Keck Osiris if I were to move this to about C 1.5. And so you can see that the separation is maybe barely, but actually is detected. And so what we then want to, but with the resolution gain of about an order of magnitude going to the ELTs, we should be able to find these things routinely with even maybe smaller separations out to a much higher redshift than we can do now. So to visualize the parameter space I'm talking about, here's a plot showing the redshift versus the projected nuclear separation of all the dual AGNs that were previously found with optical or other methods. And this something over here is probably GC 6240. And so with the next generation near-infrared IFU instruments, we're going to get down to several milliarc seconds resolution, and we're going to be opening up all this parameter space that we can hopefully explore with the ELTs. Okay, so in summary, I hope I've shown you how we can gain insights into the inner kiloparsec region of the gas dynamics, and study that using the 10-meter class telescopes and also reverberation mapping. And I think the future of where this story coevolution of galaxies and the supermassive black holes is going to get more and more exciting with the next generation telescope. So I guess I'll stop there and take any questions you might have. Thank you.